In the previous lecture, we discussed that a lot of notations when we are forming these symbolic equations, which is in the method 2, can actually be removed because of order of growth, which is some of the functions might be growing way faster and we can remove that in our equations, but that was still not a very mathematically rigorous way. So in this video, we are going to define all the three all those equations that we had in a more mathematically rigorous form by defining something called asymptotic analysis tools, which include big O, big omega, big theta. There are some others which we are not going to cover in this course, but in the course we want to concentrate on just this big O notation, and we also want to concentrate on what we call worst case analysis, because we care about our algorithms working in extreme conditions, which is we don't care what will happen if we let's say if we are doing a linear search, we won't care that, oh, we are finding the element in the first place. We truly care about what happens at the extremes, which is what if the element does not exist in the array? Then we have to do a whole scan of the array to find an element. So before we proceed to this mathematical definitions of big O, big theta, and big omega, let's discuss what asymptotes are. You might have seen these in your previous classes, but basically asymptotes are functions that run very close to another curve for very large input size n. And what I mean by that is, in the earlier set of videos, we defined that we have this n getting larger on the x-axis and the time on the y-axis. So the asymptotes are functions that run very close to each other, which is like these are like two different curves. They don't meet each other, but they run very close to each other. And why this is important is because for very large input sizes n, let's say if the one of the curves is represented by n and the other one is represented by n plus 1, we can get rid of this plus 1 because they are very close to each other. So what we truly care about is, like, let's say if this dotted line was an approximation because it was n, and the other one was n plus 1, that the difference in time delta t, which is delta t, is so small, it's almost zero when n tends to be very large. And that's why this notation is used. We are going to see very soon the instantiation of this notation, but basically we are concerned again with the tail behavior, which is what happens for very large n, which is when n tends to infinity. So let's now formally define what is big O. A function t of n is called, or it belongs to the set of functions big O of fn if there exist two constants, which is n naught and c, and both of those constants are positive, such that tn is less than or equal to c of fn for all n greater than n naught. So this is a very mathematically jargonious definition, but I'm going to simplify that in a little bit. But the key idea behind that is, let's say if one of the we have a curve for one of the functions, and we have another curve like this. So even though the red curve here grows slower than the green curve for small n's, after a certain threshold, which is after this n naught, this grows way more faster compared to the green one. So, and after this n naught, there will be no way that the green curve will grow faster than the red one. I think I should use some other color maybe, because some of you might not be able to see red and green differences. So what I'm going to do is I'm going to change it to blue and red. So we have this blue curve that's growing this way, and there's the red curve. So after n naught, which is a certain constant, this curve overtakes that one, and then this red curve will always bound this lower curve. So basically, O of fn gives us a upper bound of the total time of execution for this function Tn. Now, another thing to note is a lot of books follow this convention that they write something like Tn is equal to O of Fn. This is actually wrong. This is misused a lot, because O of Fn actually is not just one function, and this is basically a set of functions. So what I mean by set is, like, let's say if the Tn, the time that you calculated, was something like n plus 4. So an upper bound for this function would be something like n squared. That could be an upper bound. So is n cubed. So is n to the power 4. So is 2 to the power n. So is n factorial. Because n plus 4 can fall in any of this set of functions. It's not just one function. Now, n naught and c here in this definition, what it means is, like n naught I already explained to you, like there's a point where one of the curves will start to grow much faster, and c is basically another like constant that multiplies fn. So in this case, this was fn, and the below curve, the blue one, was actually tn. So basically the fn could be even fn, or it could be a constant multiplied by fn. And again, what I mean by a constant multiplied by fn, which is why this is useful, is because let's say if your function was n, like 2n, then if you want to have that function belonging to O of n, uh, it like 2n will grow obviously much faster than n, but there might be some cases where this it also belongs to O of n, because if you multiply with a constant, like if I multiply n with 3n, it's still in the same family of curves. So therefore this tn provide, like fn is like an upper bound on this function tn. And what I mean by a tighter upper bound is, like this term, that tighter upper bound, suggests that although this n plus 4, the tn, can be in this entire set of functions, which is n square, n cube, n4, we want to use the most tightest one, because the lowest one might be n, because this n plus 4 might belong to the same curve as n, given this definition. So we want to suggest the most lowest of all the upper bounds. Like although n plus 4 can belong to n square, 2 to the power n, and so on. The lowest one it can belong to is n. So throughout the course, we'll try to do something like n. Otherwise, like every function that we see in the course belongs to n factorial. And if you say that, oh, what is the time complexity of this? You can say that, oh, it's n factorial, O of n factorial, and it will be correct because it's like an upper bound. But what we are concerned about is to have this n our function to be bounded by n plus the tighter upper bound. Similarly, there's another notation which is big omega. It's again like pretty similar. The definition is exactly the same, but now it's the equation is actually swapped, which is now instead of less than equal to, it's like greater than equal to. And what this basically means is, again, if we have a curve like a red curve that's growing this way, and we have another blue curve that grows somewhere like this. So here, this Tn, the blue one, is your Tn. And the red one is your Fn, sorry, Gn in this case, because it provides a lower bound, like after a certain threshold, which is n naught, the minimum amount of time that would be taken could be represented by this family of functions, which is called g of n. So this omega notation basically provides a lower bound instead of an upper bound on the growth of Tn. Also, again, like we are going to say that we'll be using the most tightest lower bound, which is like, although if we have some function that is something like n square plus 4, we can say that this belongs to n square, it can also belong to n, it can belong to 1, it can belong to n to the power minus 1, and so on, or n to the power minus infinity as well. But what we are concerned about is the lowest bound, lowest title bound. The last definition we are going to discuss is the big theta. So this actually provides a, a notation for a family of curves that provides both an upper bound as well as a lower bound, which is if a function grows like this, then there could be two other functions. One of them grows like this, and then another one grows like this. And then after a certain threshold, which is this has a certain threshold, this function, the red one, is bounded by the growth of these two other functions. So that's why we have two different constants. You don't need to know all these definitions, but what you need to know and understand is what big O is and what's the definition for that. In this case, it provides a threshold for these two functions. So the middle one here is t of n, and the other ones are basically g of n's and g of like g1 of n and g2 of n. So I'm going to discuss a quick, this is a quick neat table that summarizes all the information. So big theta provides an order of growth, which is of fn, while big O provides an order of growth which is less than or equal to fn. I want you all to fill this one out, which is what big omega provides us. And here big theta provides us with like a family is given, which is theta of n square. So all of these functions, n square divided by 12, 2n square, and n square 11 plus 11n, all fall under theta of n square. While if we talk about O of n square, since it's an upper bound, all these will fall into O of n square. Even O of 1 will fall in this, or O of n will fall in this, and so on. So try to fill this out, and we can discuss this in one of the solutions, like in one of the office hours. Finally, let's talk about a little bit about some of the growth rates of some of the functions. Like in this case, we have this program which has just three definitions. We have we are defining a variable that has cost 1 in our notation for symbolic notation in the method 2 that we learned. Then we are just incrementing this, and the third one is returning. So these have like constant costs. So if you increase the size of this n to maybe 1,000,000,000, nothing will happen. The program will still take 3 units of time. And therefore, this cost function, which is for any large inputs, the time remains constant. So this is categorized into O of 1 because the processing time is independent of the number of inputs. Like in this case, we have Tn equal to 3, and then Tn belongs to O of 1, which is a constant function. Let's see a few others. I'm just showing you the most common ones, and then I'm going to summarize the detail for like more mathematically more jargonious functions, which we see less often. So for the linear growth rate, it grows proportionally to the number of inputs, n. Here we have this one for loop where which runs from 0 to n, and we are basically running the sum of numbers from 1 up to n. So this formula, again, you're going to see a lot in this class, which is what is the sum of first n natural numbers. This is basically given by n times n plus 1 divided by 2. I can, if you want, I can show you how this formula is derived. It's pretty simple, but basically you have all of this, and then you can rewrite this and deduce this formula very easily. But the key idea is, like, if the loop is running from 1 to n, the majority term for this analysis we have already seen is 3n plus 4. So this is categorized in Tn. The Tn is in a family of big O of n. And why we can do that is because if we take a constant, which is 4 in this case, like it could be any constant, it's not just 4. Even if I take 5 or 6 or 7, I can easily find out for what n naughts will this curve beat another. And how you typically do that is you have this one of the curves, you have a straight line, Like let's say if you have a straight line, you basically find the intersection of those two lines, which is you have two equations and two unknowns. Like let's call one of the equations 3n plus 4, and the other one maybe like it's a parabola or whatever it could be. So you have to find the intersection, and that intersection is basically the C. I'm not going to derive this. I can show you maybe in Monday's lecture how to derive these numbers, but it's pretty straightforward. So this function grows linearly with time, which is like if the n becomes a trillion, y basically becomes a trillion, and you'll get graphs like this. The next one is quadratic, which is this is seen in two for loops a lot, but let's say if there were two for loops, there's no reason that it is like n squared. Like if these numbers are something else, which is this is growing something else, you need to make sure that this is not n squared just by like if you see two for loops, don't just jump to the conclusion that this is n square. That's not the case. You have to analyze it by seeing what is the complexity for the inner loop first and then going outward. So in this case, this is a very easy example because it's running from 0 to n. So the inner loop will run n times and the outer loop will also run n times. And hence, how it's going to do is, let's say if the inner loop is running n times, so you run the inner loop n times and then the outer loop, like this n plus is repeated n different times. So you get basically n squared, because the sum of it might will definitely lead you to n square. So in this case, you can see that the function y is actually growing quadratically, or like if it's a polynomial, any sort of polynomial, it will grow more faster than a linear runtime function. The last one is logarithmic, which is let's say if I increase the loop instead of by 1, let's say if I increase it to 1, 2, 4, 8, 16, this is actually growing exponentially. So in this case, we get logarithmic growth. And in the next video, I'm going to show you like how to prove this. But right now, you can think of it as this grows much more slower than another, like a linear or log linear or a polynomial function. So these are some of the different growth rates. You can see like I calculated the input n and what would be the time and in which order or which family do they belong to. The general key takeaway that you want to take away from this is that constant time functions are much slower than logarithmic, which are further slower than linear, then which are slower than log linear, polynomial, and then exponential and factorial. In this class, we'll just be concerned about, mostly we'll be concerned about this class, all these classes of algorithm, because after that it gets very complicated.